Let's go ahead and get started. I think the primary goal today, although we started to dive into this on Tuesday, is just kind of provide a little bit more clarity with regards to, we know ultimately in the geometry stage, there's this matrix that we're multiplying all of our vertex positional attributes by. And for a lot of what we do, that's probably sufficient, right? For implementing the underlying architecture, that level of knowledge is probably sufficient. I just want to try to connect what we already talked about, which is how one can construct a matrix to do things like shifting a vertex or scaling your geometry by multiplying your x and y coordinates, and how to connect that to what does it mean to actually just view a scene in practice. At the end of the day, I think primarily the focus of this course and what I hope you take away is how to be an appropriate practitioner of that, not necessarily be able to derive from base principles how we construct these matrices. Because as practitioners, I think it's okay to rely on well-established, well-vetted functions for doing that generation of those matrices for you. So I want to talk more about viewing, and the term you will hear used is so-called classical viewing, either historically or through sort of the field of architecture or just classical photography as well. What does it mean to view anything? What does it mean to view a scene? Requires three basic elements. There's the actual scene, one or more objects you're actually interested in viewing. There needs to be a viewer. This is our camera model or our human eye or the person viewing a scene with a so-called projection surface. This is a synthetic concept, but it has a very real analogy in the human visual system. That would be like your retina, where your light gets focused through your lens in your eye, gets projected to your retina. In a camera, the closest thing in a digital camera would be like the CCD or CMOS sensor array that is capturing the light as it comes in. And then as, again, a synthetic view of what's happening, you have this concept of projectors that go from the objects to that projection surface. Any of you who've kind of explored around and dug around the concept of ray tracing and ray casting, it's kind of the exact opposite of that view, of that way of thinking about how we view a particular scene. So when we talk about classical views, and there is a large taxonomy of different classical views, of which I think there's kind of limited value in going into that in much depth, it's really talking about the relationship between those three elements. The viewer picks up the object and orients it how they would like to see it. They then also select the projection surface and how those projectors are arranged from the objects to the projection surface here. Standard projections then project that image onto a plane, and the projectors are lines that either converge at some so-called center of projection, like shown in the right-hand figure here, or that are just parallel to the projection plane, as shown in the left-hand figure here. The parallel projection has quite a bit of value for computer graphics. In terms of where you would typically see them used, though, it would typically be more for architectural or engineering drawings or CAD drawings as well, where we don't necessarily care about sort of human realism of the object we're looking. We're trying to accentuate some aspect of a building or some other piece of architecture or a CAD model of something. Whereas when we want something that's more realistic, because that's how our own eyes see the world, we are going to want to have those perspective projection where we have a center of projection. Again, think of that as your retina or your camera sensor, and as projectors are visualized as coming from the object to a projection plane, they are converging at that center of projection. Here are some just examples, and I won't bore you with all the taxonomy of classical projections. What you should be able to tell in looking at this, although I didn't as formally say it as such, is which one of these are parallel projections and which one of these are perspective projections. One way you can determine, although this is again just a image in the first place here, you can tell if it's a parallel projection if lines of parallelism that you'd expect to be there in the actual object are still all represented in the render, the two-dimensional viewing of that object. Whereas in a perspective view, there would be at least one, but potentially up to three vanishing points in which things, if you imagine extending that out into the far distance, would appear to be zero, would appear to be very minimal in size. So some of the names kind of give this away. So isometric is a good example. Do we think that's a parallel projection or a perspective projection. It looks parallel to me, right? Now, again, we have to assume that this is a classical column, Greek architecture, so that there would be lines of parallelism. So in reality, these columns would be parallel to each other in reality, and then there also appear to still be parallel here in this view. Similarly to like this kind of steps or curves that we have here, those would be parallel to each other, and they appear to be parallel to each other. That is generally not how we view a piece of architecture. If you were standing at an equivalent angle, looking down at the Parthenon or something, and trying to see what it looked like, it wouldn't look like that to you as a human observer. Now, with your camera, there's certain lenses you can buy. You can do telecentric lenses, telephoto lenses, anything that is a sufficiently long point of projection can give you something very similar looking to that. It's not an infinite point of projection, but it's good enough from how we would be able to view a particular object. As compared to that, we have, the front elevation is also parallel, right? Orthographic view here, in that you don't see any kind of depth to it at all, because all those things that are behind it are in parallel with the things we're currently looking at. They're completely occluded by what we have closer to us here. We can compare, and maybe you get a feel for what the concept means when we compare the 1-point perspective to the 3-point perspective. Those are vanishing points. Those are objects that are actually focused off to some point at some reasonable distance that are disappearing to zero at that distance. So 1-point perspective, the dimensionals, I'm going to have a little trouble kind of pointing what I'm getting at here. The vanishing point is often through here, right? So as we look further back, if there was a person standing right here, they would appear much smaller in this render than a person standing on that front step here, because that vanishing point is going off in that direction. For the 3-point perspective, it would be any three, this axis, or this axis, if you can see that here, where anyone going far enough off in that direction would appear to disappear here. And I did bring up the taxonomy, but I don't know if it's, unless you're studying architecture or formal drawing techniques where one has to actually learn how to draw things with perspective. It doesn't necessarily come naturally. You have to kind of visualize where your points of perspective are going to be and draw and do the diminution of objects sort of manually if you're learning how to draw. A couple more, as I mentioned, orthographic. We already talked about isometric. Isometric just means you have this view of the object and you split each axis and give them equal 120 degrees, and you get your nice looking toaster when you do your isometric projection there. There's not really thought of as one projection being right and another projection being wrong. Depends when you're rendering a scene or drawing something, what you actually want to emphasize in that drawing. Sometimes you want to actually look and really display in this house that you're rendering or taking a photo of, you really want to display what the front of the house looks like and have it be kind of equally proportioned to what it would actually be in reality, then you may want to have a front plane oblique view of an object. This is not necessarily correct in terms of how we're ourselves seeing the object, but it depends on what your goal is in creating the render here. So it's not that one is correct and one is wrong. The nice thing, or what kind of simplifies our task, is at least in the OpenGL, and to my understanding, all other rendering systems, from the software application perspective and the underlying hardware perspective, the values in the matrix we wind up having to create to do these different types of projection are quite a bit different. And so understanding them requires a little bit of extra effort here. But the end result is something that's going to get projected to the same kind of viewing volume. So the actual hardware required, what happens when we process our vertices, is effectively identical no matter which type of projection, perspective, or parallel we decide we actually want to use here. Right, so in the real world we see things in perspective. It's the best photo I could find of someone, my son, when he was very young and being projected in front of the Washington Monument. You can tell it's an old photo. It still had some renovations done after that. It doesn't quite look like that today. Things that are actually parallel to each other don't necessarily look parallel, and there's some center projection, there's some conversion point here. And we see things in perspective, right? We talked about that on Tuesday. Joey takes after me, he's not very tall. But in this photo, he looks, roughly a third of the height of the Washington Monument, and in reality, he's not nearly that tall. That's a function of that diminution of things that are further away. This example, he wasn't that far away. I don't know, a couple hundred feet away from the Washington Monument. If he was 1,000 feet from the Washington Monument, he would appear bigger than it, right? Of course, you've always taken photos where you have a skyline of a city in the background behind you, and you appear to be bigger than those buildings behind you. And how much bigger you are, or what the relative size is a function of that relative distance between them. So we have to have some mechanism. While it seems a very natural thing that we're very well accustomed to, we have to have some mechanism when implementing our classical viewing in hardware via these matrix constructions to do so in such a way that if we have an object that has different depth information associated with it in our scene, we have the child, we're rendering at a certain z value, right, certain depth information. We have a building that we have at a different, further away z information. We have to have some mechanism that's going to transform z, our depth, into a scaling matrix. And I think if you just think of perspective transformations as doing that, that's probably sufficient. And if you got that, we can be done for today. But that's what we have to do. We may render these things in our model coordinates, right? Whatever units and coordinates make sense to model a person, whatever units coordinates make sense to model a building, they are very likely to be different, right? We model them, as we talked about earlier, probably centered at their own origin when we model them. Because this is a character model, we may want to put it anywhere we want in any particular scene. It could be flying through the sky, it could be standing in the ground. Similar for our building, it can be placed anywhere potentially in our scene. We model it at the origin, we then apply that world model view transformation to place and potentially scale our objects where we want them in the scene. No matter how this was modeled, no matter how this was modeled, presumably, we want to model this as child size, we want to model this as building size in the scene we're rendering, but now we still need that extra step. Now we're setting up this view of the scene, and even if, 2 feet tall, I'm not sure, this object's supposed to be a couple hundred feet tall, this object's supposed to be, we're taking a perspective view, we have to now do an additional scaling of those objects effectively, such that objects that are closer appear larger, objects that are further away appear smaller. So there's multiple transformations going on here, and I just want to make sure you can think of it as 3 different transformations that are happening. The first 2 are kind of closely coupled to each other. When we talk about the equivalence between modeling and viewing, we have an object, we need to make sure it makes sense with regards to where it is in the scene. There's a certain set of positional attributes that make sense when we're modeling an object, depending on how we're capturing that model, what software was used, what units and geometry make sense for that. And then separately, once that model is included with other models in a scene, we have to determine what the relative relationship is. That's the modeling matrix, viewing matrix, oftentimes combined together, so-called model view matrix. That was Tuesday. Today, now we have to select our camera and determine how we want to view all the models we have in a scene, so we can think of that as being a separate step. Taking the object, rotated, stretched, translated it. Put them all together in the scene. That's the rotation, scaling, translation. Now we select our camera. At the very least, depending on the type of camera we are selecting in our view of the scene, we have to do an additional set of steps to get it such that, for example, we have a perspective view. So things that are closer appear larger. If you got that, the rest is just implementation detail here. Sure.
So if we don't include like a camera view transformation, would it look as if it was like in that parallel view? Okay. You don't have the perspective.
That's right. So the default, and I haven't mentioned that yet, maybe very briefly on Tuesday, the default projection is an orthographic projection where everything is a 2 by 2 by 2 cube centered at the origin. That's the default projection. If you don't specify it, similar, I guess, for all of our applications up until cube flyby or whatever in MP3, that was how we were viewing things. If I set up this person and this building here, assuming they all are specified within that range, because if they're not, they would get clipped out eventually. They would appear to be basically on top of each other. There wouldn't be any perspective there. This is my attempt at slightly a joke of what it means to have perspective and not have perspective in art. This is misleading. It's not like one day people discovered what perspective was, but there's some thought that some of the early Renaissance painters were those who really kind of perfected the technique of drawing things with appropriate perspective. This is not a bad, it's a little artificial, it's not a bad mental model to have about what it means to have a parallel view of a scene and a perspective view of that same scene. You can think of it as, one looks better than the other, although that's not really the point I'm trying to get across. But when we have a parallel view, everything's a massive telephoto lens. There's two people in a scene. We talked about this on Tuesday. And in that picture of the scene, if it's a telephoto lens, if it's a parallel view, I can't tell if they're 100 feet apart or 1 inch apart, because they're going to be projected exactly the same way on top of each other. Whereas when you do have perspective, even a small amount of perspective can make a very big difference that you can determine these people are closer to the painter, closer to the camera than the people who are further off in the distance. Again, one is not better than the other, but one, I would argue, gives a more real-world view of how we as humans would view a particular scene here. So I mentioned this, that's what I was talking about with regards to these vanishing points. These are the parallel lines that are parallel in the scene itself are actually going to wind up converging to at least a single point in the projection. That's the so-called vanishing point here. When you're drawing a perspective by hand, if I asked you to try to draw this type of thing by hand, at least that's the technique people use to kind of learn how to do this before they get more direct intuition for how to do it, you would actually draw those vanishing points, and you would see examples of you would draw 1, 2, or 3 vanishing points and make sure that those are the lines that stay parallel, the things that are connecting to that vanishing point there. So that we have these, I think it's probably easiest to see in the 1-point perspective here. We have these things that are parallel in the actual model itself, and for this one, look at the left edge and the right edge of this, and they are parallel in the object as it's being modeled or visualized here, but those parallel lines now are going to converge at some point in the distance. Roughly, I guess you can kind of estimate where that vanishing point would be for this particular scene here. If you moved where the vanishing point was, that would change how those parallel lines in the model how much angle they would have, how much they would appear to quickly converge to give that perspective view of what's happening in the scene. Another way to think about that is that same effect is what allows these columns that are in front to appear to be larger than those columns that are behind. It's all directly related to each other. I think we got it. Diminution, making it smaller as things go further away, do appear to make things look more realistic than if we don't have that. So we have the 3 aspects of the classical viewing process, all of which are effectively being implemented in our graphics rendering pipeline. So we already talked about, we have to select the objects in our scene, position the objects we want to render. That's the model view transformation. Even if it's a little fuzzy to you, that's what that is doing. Take my objects, decide where they're going to be in my particular scene. Then there needs to be the actual positioning of where our camera is going to be in the scene. And there's no actual camera, but this is the synthetic camera model where we are rendering something. We're converting from a 3D object, 3D scene to a 2D render. That's the whole concept of rendering by projecting. And we're projecting through a camera that is positioned somewhere in our scene and is directed somewhere in our scene. So that is the positioning of the camera, and we talked about that can also be thought of as equivalent to, am I moving the camera closer to the scene, or am I moving the scene closer to the camera? It's the same, right? It's this relative transformation of where things are relative to each other. Now we're talking about is we're looking at perspective versus parallel viewing. You can think of that as setting the lens of your camera. And depending on what type of lens you set, on a proper camera, your telephoto lens or your macro lens or anything in between, that is going to be the equivalent step that we're going to do of setting our projection matrix. And then the other difference is based on what lens and where the camera is positioned and where we specified our geometry, we have to get our scene in such a way and our vertices in such a transformed way that we can then perform clipping. That's specific to rendering. Ultimately, when we're doing a real camera, there's a certain field of view. There's only so much light that's going to be entering the lens, and there's kind of just natural clipping that occurs. In our synthetic camera model that we're doing our rendering, we need to have a way by which when we position our camera and set our lens, the end result is something that we can perform clipping on. So it's a little different in that sense that we're not just specifying position of camera and type of lens, so field of view of our lens, of our camera, parallel versus perspective projection matrix we're specifying at that point. We're also specifying what amount of our scene do we actually want to have represented in the final render. So that part is kind of artificial and or unique to doing 3D rendering, where we're also then specifying what is valid. Of all the things we've positioned in our scene, transformed in our scene, what do we actually want to have represented in our final rendering? We talked about clipping already, clipping lines and clipping primitives, and that operation is still exactly the same. Most, if not all, rendering systems use this process to transform all the geometry so that performing that clipping is easier than it otherwise would be. So what we wind up actually doing, as I mentioned, we have this default view where if you just specify the identity matrix, your viewing volume is this 2 by 2 by 2 cube centered at the origin. The end result of all these projections that we're going to be applying is that everything winds up getting transformed into that 2 by 2 by 2 cube. After all these projections are applied, anything that doesn't fall within that cube is what winds up getting clipped. So it's a little bit of a chicken and egg kind of description of what happens there. Clipping, we kind of generally have a high level intuition for what's happening there. Clipping is made easier by this designation that we're projecting into a clipping volume for which, if it's greater than 1 or less than -1 in any dimension, then we're going to perform that clipping. That's also then what happens by default here. Are we okay? How are we doing? Okay. I just want to make sure. I realized I was talking quickly there. I get excited about this. So, okay. And I have another one of those demo applications. So if it starts to get too abstract or not sufficiently interesting to you, we can kind of jump and just kind of get that intuition for what's happening in practice again. So I mentioned this, let me just mention it one more time. By default, there is always this matrix that's getting applied in OpenGL, but it's an identity matrix by default. So what does that mean? When you have the identity matrix, you take your input geometry and you're not really changing it at all. A proper vertex shader, which is a requirement to have, at the very least is doing a pass-through. And that's what we've been doing all semester. A pass-through is the same as multiplying by an identity matrix. What that effectively means is that that entire set of transformations is, by default, you do nothing. You just pass through the geometry that you specified. Is that what that means in practice is that you do have a camera always. We just don't think of it in those terms, but you do have a camera always. It's just located at the origin. And by convention in OpenGL, the camera is pointing down the negative z-axis. That is an OpenGL-specific convention. Direct3D does it differently. OpenGL also, by specification of the language API framework itself, specifies also that your default view volume is a cube with sides of length 2 centered at the origin. So not only is the default model view matrix an identity, the default projection matrix is an identity, and clipping is performed against that cube. That I would call by spec. That's not a mathematical requirement, that's the case, but that is the spec for OpenGL, that is where our geometry is. So why have we been able to see the red triangle? What did we do? We specified just pass-through for our vertex shader, so an identity matrix for model view and for projection, and we made sure that our geometry was falling in that -1 to 1 range, and we were able to view it because we kept our z value at 0. If you made your z value 0.1 for any of those vertices in your red triangle, until you get your matrix stuff working, we wouldn't be able to view it. You wouldn't see it either in your OpenGL window, or you should not be able to see it if it was implemented properly in our hardware. That kind of yeah. I thought that was kind of because why was our stuff still working? Well, part of that's always a compromise with what we can present in terms of a lab experience, but to kind of delay having to do this kind of math in the hardware basically as late as possible, while also having the goal of it being, a 3D graphics class and not a 2D graphics class, which would also be really fun to teach as well, right? We could just do a sprite processing class and make Nintendo-style video games all day. Let me know if interested.
Yes.
Okay. That's one. I need a couple more. I need a couple more to make it work. This is just a visualization of what I was talking about here. So your default projection is orthogonal. Your default viewing volume is this 2 by 2 by 2 box centered at the origin and actually the camera pointing down the negative z-axis here. So anything that falls within this cube is going to get projected to that projection plane. That's why we get a nice red triangle, for which z information is not irrelevant per se, but as long as it falls within that range, it's going to get projected onto our screen. If we want to move our camera now, which in theory we do, if we want to either just visualize an object that has both positive and negative z values, we can do a translation of that camera. Let's move the camera away from the origin. Both of those views of either moving the objects to the camera or moving the camera to the objects, they're equivalent, and you can do that via that model view matrix. We kind of talked about that on Tuesday. You can set the matrix manually yourself. OpenGL used to have a call like GL translate where you would specify where you want to move things to. Now we tend to use third-party libraries, but effectively have the same API type of interface where we're specifying we want to do a negative D translation. We want to move D units in that Z-axis. Also provides the function called lookAt, which you may have played around with a little bit for cube flyby. This also was effectively equivalent to an old native OpenGL viewing function, but now it's provided via the GLM library here. And it forms a model view matrix through a relatively user-friendly interface. Definitely once you start to use these functions, you do have to start to think about, okay, no longer am I just taking triangles and hoping my XYZ makes sense, and when it doesn't work, I try again. Now you have to have a 3D view of what's happening in your system to be able to do these kind of functions that we're going to start using. So look at is exactly what it sounds like. Position a camera, tell it to look at something. And then separately, because that's technically ambiguous, also define which direction is up for that camera. So if you think of like 3 degrees of freedom, we're positioning it, we're telling it to point in a direction, that's 2 of our degrees of freedom because it's both X, Y, and Z information there, and then determine which way is up. That's kind of the rotational degree of freedom here, and you're basically passing it 3 vectors. So if we had a cube that was centered at our origin in our model view coordinate system, when we've modeled and have it in our scene, like in cube flyby, it would not look appropriate if we didn't have our camera located somewhere else. With an orthographic view, if everything was still centered at the origin there, you would see something. It would be all the triangles of it kind of laid on top of each other. It would not look like a cube, I can at least tell you that. So in order to be able to actually see the cube, we have to be moved. Either move the object, move the cube, or move the camera away from the cube. And one way we can do that is by calling that GLM lookAt function. Now, it's a little ambiguous the way I'm phrasing this here. You have to call this function returns a matrix. You then have to pass that matrix via a uniform value to your vertex shader. The vertex shader then has to do that matrix vector multiplication to be able to get this equivalent transformation. But the OpenGL interface is basically this for doing that. So we specify IX, IY, IZ, I, or camera location, XYZ. So I'm putting my camera at location 1, 1, 1 in my XYZ Cartesian plane here. I am looking at something. In this case, I'm looking at the origin, which would be I'm looking right to the center of the cube here, and I'm defining up as in positive y-axis. And for the cube, it would look different if you were to change this up vector. It really depends on what you're doing, but this is a valid way of thinking. Up is what up is when we were thinking of x, y, and z. So we have to position it somewhere outside the cube, look towards the cube, and determine which way is up. Don't think there's a shortcut to just kind of thinking about these issues by trial and error. Starting with a cube isn't a bad idea to start in terms of what does your viewing look like. We have to eventually do that projection. So the term projection really means dropping of dimensionality. In our case, it means going from 3D geometry to eventually 2D geometry. So the default projection when we have that 2 by 2 by 2 cube is a parallel projection. Effectively, if you're within the viewing volume, you are dropping Z. Now in practice, we don't actually drop Z initially right away, because we also now know when you have lots of geometry in a scene, that depth information is important to keep basically as long as possible, so you can determine the relative ordering of your objects. You don't have to draw in a particular order. So we are dropping Z in terms of how things are going to get projected into X and Y in our window pixel coordinates here. But we're still keeping that Z information because that'll go into our depth buffer, and all the stuff you're doing for MP4 still exists. But logically, you can think of as a parallel projection is saying, with this default kind of orthographic view, you're just getting rid of Z entirely, assuming it's falling within the clipping window here. Most graphic systems use this concept of view normalization, that if you have any other view of the system, the transformations you apply for those views are intended to transform it into that same cube, into that same default viewing volume here. So when we talk about for a particular projection today, what does it mean to apply that projection? Mathematically, that's what all these constructions are doing. We have different viewing volumes we are interested in. Could be just as simple as we have still an orthographic view and we want to move it 5 units to the right. Fine. The transformation we apply as part of the projection matrix is how do we move the geometry effectively so that it gets us back to that 2 by 2 by 2 cube. So you can think of it as a scaling operation, a translation, potentially a rotation operation, and a combination of those that we are applying to do our projection. And that's why we think of this as not just having 1 or 2 matrices, but ultimately it's kind of 3 matrices we are generating here. 1 for modeling, 1 for viewing. Again, you can think of those as being an analogous operation, so just having a single matrix and then a second matrix for our projection. So when we talk about the MVP transform, that's the name of that shader that we're using for cube flyby, and for anything 3D, you'll want to use something similar. MVP is model, viewing, and projection matrix. We do it just as a single matrix as a design decision in hardware to recognize, well, we have these 3 matrices, 1 for modeling, 1 for viewing, 1 for projection. We need to multiply our geometry by all 3 of them. We can just do that multiplication of the matrices once per frame. Do all of those matrix multiplications once, then just pass that final singular matrix on. But it would also have worked if we instead were passing 3 matrices on and doing all that stuff in our shader hardware itself. So for our default orthographic projection, I said we want to keep X, keep Y, and just drop Z, with the caveat that logically we're doing that. In practice, we do still want to eventually keep Z so that we don't lose our depth information here. But for a single triangle in isolation, this is a valid way of thinking about it. So our matrix can just look like that. Don't change X, don't change Y, don't change W as well, and just drop Z entirely. That would be one way to do it. You can think of it as a 0 scaling in the Z dimension, because that's kind of what's happening here, right? No matter what our Z information is in our geometry, when we have this parallel view of the scene, we're basically scaling that all to 0. No matter how far away you are, you're the same distance away. When we have a perspective projection, it gets a lot trickier. So we have our virtual camera. It has some concept of a lens with a field of view, and what we're actually setting up now is no longer a cube but a frustum, so like a truncated pyramid where we're specifying a near clipping plane and a far clipping plane, and there's lots of different ways you can do that specification. You can specify it based on the field of view, the actual angles themselves, or you can actually specify them based on manual specification of this rectangle and this rectangle in 3D space for the near clip plane and the far clip plane. OpenGL lets you do it either way. I mentioned foreshortening. What does this mean in practice? As I say that things that are further away should appear smaller. Things that are further away, meaning larger Z value, should be scaled such that they are smaller. If we got that, the matrix that has to be constructed, at least conceptually, is relatively straightforward. But this view, I think, is kind of unnecessarily complicated, right? We have a projection plane of D. Certain objects are a certain distance away from that projection plane. The further away they are, the more we should be inversely scaling our X and our Y for all the geometry at that location of Z. So we would have to do some sort of division. And one way we can do so, is not with our matrix itself, is to recognize, well, okay, for a particular, this is the top and would be also the side view of it where we have our projection plane. You can't really visualize it very easily in 3D. We have our projection plane, we have our specified geometry. As we project our x and separately our y onto that projection plane in z, there should be an equivalent scaling of our x and y values by that amount we are off from z, how far away we are from z. Z is going to get projected to that projection plane of D. X is going to get scaled by how far away we are from Z, and Y is going to get scaled by how far away we are from D. That division at first blush doesn't sound like something we can do with our matrix formulation because that's all multiplication and addition, right? There is no addition as part of it. It turns out that if we set up our projection matrix like this, where we're now using the homogeneous coordinate system, using our fourth coordinate here to scale these values by a function of D, we can actually just pass in x, y, z. We wind up then scaling not any of those values, but the value of w by z over d. So notice this element is in a place where we haven't been putting any matrix elements as of yet, right? So this would be w, assuming it starts off at 1 here, is equal to that value of w times z over d. That doesn't get us the scaling by and large itself, but there's then this extra required step. And here is why the step is there. It's not there for any other reason other than to perform this division for you. If you do your transformation and you wind up with the homogeneous coordinate, your w coordinate not being equal to 1, to get our geometry back on the same Cartesian plane we originally started with, we then actually have to do that division ourselves. We have to take the resulting values of x, y, and z and divide all of them by w. Because while we talked about how there's an equivalency between this point and this point in our homogeneous coordinate system, ultimately we care about the actual xyz1 coordinate system in which we were specifying our geometry in the first place. How do we get back to a value of xyz1 is by dividing our w value by z over d. And that's what we wind up doing. That is a manual step that has to happen. Whether the shader kind of auto-generates that division, whether we ourselves add the division step in the shader ourselves, or whether there's fixed function hardware to do this perspective transformation is an implementation, specific decision that you actually get to make if you want to be able to do prospectively correct transformations.
What's the reason that we scale w instead of just scaling the x, y, and z initially?
It's a little hard to do the scaling of x, y, and z initially with this matrix formulation. My argument here is a little tautological. It's a little circular of an argument because this whole setup is intentionally for this reason. It's not a coincidence that it works out this way. If I want to divide x, y, and z by, or x and y by z over d, you're also dividing z by z over d, but I want to divide x and y by z over d, it's kind of hard to do it with just the basic matrix formulation. You can multiply it by z. You can get x multiplied by z in something, but dividing it by z isn't really possible with a matrix vector formulation. You're only multiplying and adding stuff. You're never really dividing stuff. So that's what we wind up doing. We wind up multiplying w by z over d, which also doesn't do the division for us either. There is then this extra required step, the so-called perspective division step. That is part of the viewing pipeline, part of the geometry stage of our graphics rendering pipeline, and is necessary to get a perspective view. Again, I think logically it's okay what's happening in terms of things that are further away. The larger my value of z is when I specify it, or further away from my viewing plane, but larger z value after considering the viewing plane, the smaller my x and y should correspond to at the end of the day. We want the building to appear to be relatively small compared to the child in the foreground. That building is going to have the much larger z values further away from the camera. If we were to do a parallel view, there's no problem. We ignore the z information altogether. Everything is like directly on top of each other. But when we want to have a perspectively correct view of the scene, that division is a requirement. And it is just kind of a separate step. It's part of the matrix formulation, but it's something that has to happen after the fact. that you do all the matrix processing steps, you do your MVP matrix vector multiplication, and there has to be some step that then checks whether you code it into the shader, which you could do. We have division instruction in the shader. Whether some driver fun stuff happens where it kind of gets auto-generated as like additional driver code. I don't actually know in practice how it works given an NVIDIA or AMD driver, or whether there's just still a separate piece of fixed function hardware like our rasterizer that does that division for us. Either way, it still has to happen if you want your objects to appear, realistically 3D. And the only downside, if you want to think of it as a downside, it's also an upside, right? The initial graphics hardware, what SGI became very famous for, was basically VLSI engineering more than anything else, right? The software side was almost like a side effect, a necessary piece of software and libraries that had to be written to use the hardware they were creating. Part of their big innovation was how to do floating point arithmetic efficiently in hardware, multiplications as well as divisions, to be able to do 3D computer graphics in real time. And division in hardware, and this is something you may not have picked up on in prior classes, or maybe you have, is, although it doesn't seem intuitively any harder than doing multiplication, which you can do in an undergraduate course without too much effort, it is quite a bit harder than doing multiplication. There are many different approaches. Most of them are iterative approaches. Unlike in multiplication, where by and large, given a certain size multiplier you need to build, there's just a series of logical steps that will always get you the correct solution. With division, with fixed or floating point values, as we may know, the math gets a little tricky, right? The relative ranges of your numerator and denominator may be such that there's in fact no guarantee there isn't even a solution, right? You divide by 0, what solution should you get? You divide by an exceptionally small number, what sort of large number should you get back out? The IEEE 754 and other floating point standards kind of speak to how that should happen in practice, but then the resulting corresponding hardware for it winds up being fairly complicated. And as I was thinking about this slide today, this would be kind of fun to learn. So I have a slide here on SRT division, and it's kind of fun because it's not you don't use a binary representation anymore. You use -1 and 1 for 0 and 1 as you're representing the digits here. And then over time you group the digits together and you do multiple bits of division at a given time. I think for today, for division, I think a sufficient takeaway is division is hard. That's one takeaway. I'm fine with saying that. Relatively hard, relatively resource intensive. You always already, I think, in your designs have to think about, okay, I'm going to add another multiplier. That's going to start using up FPGA resources pretty quickly, and division, many more than just doing an additional adder, which we, given FPGA today, we hardly even think about sometimes. Division, as multiplying is like an extra, order of magnitude, it's n squared versus order n operation. Division itself is another order of magnitude on top of that as well in terms of resources, or at the very least in terms of time it takes to do that division. Because the approaches that we still use today in sort of state-of-the-art dividers are iterative and they require successive estimation. You may not know Newton-Raphson, or certainly probably not Goldschmidt dividers. Do you remember Newton's method for doing, evaluation of a derivative? It's the same kind of approach. You start with an initial estimate. If you set your numerator and denominator correctly, you have a reasonably good initial estimate, and then you perform a certain number of estimations, iteratively so, to eventually converge to a result that is as close as you specified that you need it to be. I mentioned even Xilinx has trouble with this one. Well, we've seen that, right? By and large, if you want to do addition in your data flow or behavioral logic, you say C equals A plus B. Trust the tools, they'll do a better job than you will on the adder. Likewise, by and large, outside of some kind of obscure use cases, you need a multiplier in your design. You do C equals A times B. The tools do a pretty good job of generating that multiplier for you. That is not the case in division. You cannot do C equals A divided by D. And I don't necessarily think there'll be an easy spec for that anytime soon. It's not a syntax issue. It's not like the tools aren't smart enough to recognize that symbol should correspond to a division. It's that the trade-offs for division are much more stark than they are for multiplication. Xilinx, just to give an example, as a company has decided multiplication, multiply accumulate operations are critical enough. Having lots of these units on chip makes a lot of sense. Unless you want something different, they'll infer those units and use those units you have on chip. For division, and this is just a really blurry screenshot of the IP core generator for division in Vivado, there's a large range of potential usages that you can have, different trade-offs in terms of how many resources the divider is going to use, how many cycles the divider is going to use, and along the way, which algorithm is it using to get to those kind of results. So because that trade-off, I think, is pretty stark for division compared to multiplication, generally, if you need division in your design today, and I don't see this changing near term here, you're going to be working with IP core generator, and you're going to have to determine what's a reasonable trade-off for you. I don't expect you to necessarily have that intuition, is 16 cycles bad or good for us? Well, my suggestion would only be, we're going to run into resource issues pretty quickly with your projects. So choosing the smallest possible divider in terms of resource usage is probably still your best bet, the one that takes the most number of cycles. And you'll say, well, then that's going to make my thing very slow. My pipeline will really be bogged down. But it's pretty bogged down already. You saw the code that got emitted for pass-through, right? Just taking the attributes and passing them from input to output was some 35 instructions, right? It's going to be really slow. And that was per vertex, where you had maybe 3 vertices you're rendering. Now, once you do that per fragment, you maybe haven't done the napkin math of what that means. But if my big red triangle is going to generate 500,000 fragments, your performance is going to be exceptionally slow. So that's another little debugging tip for MP4. You may think things are locked up, but they might just be slow. So having some little status register in your fragment shader that you can monitor, so you can actually check, it's actually doing what I think it's doing, or it could also be in render output status register as well. It's actually in the process of writing things to memory. If you've done your frame buffer switching properly, it's going to look stuck until that first frame gets rendered. So maybe your first frame should be a very small triangle, no matter what else you're doing. But a quick show of hands. I did review everyone's project proposals in Canvas and provided some pretty high-level feedback. Take until next week, and if you choose to, because it is your choice, provide just an updated rubric. And I said that to essentially every team. I think only one team's rubric was pretty much 100% spot on. Update just that part, and just be more specific with the kind of things you want to deliver on. For some of you, I just made some suggestions, and I said things like, well, you have your task split up this way, and that's valid, but I'm guessing this task is going to take up that much more time, and so give yourself more credit for it. But at a high level, everyone's project proposals are fine. How many of you think you're going to require division in your hardware? I can't, so the problem is I forget who's on whose team. How many teams does this represent? For anti-aliasing, will it require division? Division by a constant. Division by a constant, so that's okay, that we don't have to worry about. I think everybody else but your team is going to require to get additional division working. So don't be afraid of it, generate an IP core. You probably need to have one person who takes a day and says, okay, I know we have to do division, let me make sure I understand what the heck is going on with this, because they are just more complicated. They tend to be non-sequential as well, where there's a ready and a done bit associated with this, and you can partially pipeline but not fully pipeline them. So you pretty much need a separate state machine or separate control module just to interface with these dividers. There is an example of that in the rasterizer. The triangle setup code does do exactly that. Well, you'll need a divider for that as well. So you will need to use a divider for your line rasterizer for the same exact reason. I wouldn't want to try to reuse. You probably could reuse the triangle setup to also be line setup. But it's more likely that, you'll break that for a long period of time, which can be very frustrating. So I would just copy paste and then, make your own separate version. So that will require a divider. But I think for the rest of you will definitely require one. A couple of you, I think, multiple dividers for what you're going to need. You're going to run out of resources pretty quickly. Instead of going through an algorithm and doing it paper and pencil, I think that's probably sufficient for talking about division. That the step requires it. And if nothing else, if you want to do 3D geometry with perspective, it requires it for this reason. And it's separate from all the matrix vector multiplication that we are already doing. Now some of that discussion that the one group was talking about with regards to the cube flyby, which was, if you have a perspective view, it looks kind of wonky, but if you change it to an orthographic view, it actually seems to work pretty well in hardware. It is effectively for that reason. I didn't go through all the matrix calculations here as of yet, but for the orthographic view, kind of by design, you're dropping z, you're ignoring z, you're not dividing by z at all. So when not having that hardware in place, as we currently do not have in place, it still looks correct in hardware, whereas any amount of perspective is going to look slightly off. The tricky part, though, is it's very hard to reason about how off it's going to look. Because it depends on where our camera is located. So if you change that cube flyby and you move that camera, not 111, move it to 100, 100, 100, then those z values are going to be significantly larger. So the amount of perspective foreshortening is going to be significantly more. It should look much and much worse as you do that. But for the way we set up cube flyby, where the camera is relatively close by, and there isn't that much perspective in the sense of how much we're having to do division, those values should be roughly close to 1 for certain of the coordinates. In the range, I have to think about what the range would be for that. The camera at 111 and a cube of size 1 centered at the origin, between 4 and 1/4 or 3 and 1/3 would be the range for that. It probably still looks kind of okay, even if it's not technically correct. For any of you doing texture mapping, this also comes up in this situation as well. For MP4, don't worry about it, I think is correct advice. But for texture mapping, we actually have the same exact issue, where our geometry, if it has perspective, we need to effectively normalize our coordinates based on how much perspective we have here. For positional attributes, we also have to do so for our texture coordinates. Once you have the divider in place, just reuse it for that purpose, but to get your texture mapping to look correct, you're kind of going to have the same issue. Just like, our building doesn't look right if it doesn't have that perspective foreshortening. Any texture we apply to that building will also not look correct if it doesn't have that equivalent foreshortening happening in the texture mapping itself. So before I dive into, and I think we can also leave it with this quick demo as well, let me just show just in practice what it means to have this perspective versus orthographic view, because I just worry that it's just a little too abstract otherwise. I personally like to have this or equivalent. There's quite a few web application versions of this as well. I kind of like personally having this demo open as I am playing around with the matrices that I'm generating. Again, it's all the same. This is the one from Tuesday. It's all the same functions that we are using, and there's different functions for perspective versus orthographic views. But what we have to wind up doing, and there's my friend again. Let's change the model. We do need something with perspective here. Dolphins, why not? No, they look really bad. Okay, back to Al Capone. Fine. At first blush, this does look very similar to the last application, because that last application was also setting up a perspective view just as a default kind of view here. This one allows you to change what your perspective view is. This is using the older school third-party API functions, but they're effectively equivalent to what they are now. So for example, we can change where our camera is going to be located relative to our model. We have to move it off the origin, presumably because our geometry is specified at the origin. And if we have our camera at the origin as well, we're kind of inside our object here. But we can also move it to the left or to the right and change where we are looking. I want to look to the left. That can be thought of as a tilt or a rotation here. And again, I haven't talked about, and frankly it's a little bit dry, what does that mean from a matrix perspective, how one would manually craft the equivalent matrix. It'll be nice to see it once, I guess, but then you're using these functions and it's generating the matrix for you. So I don't want you to get too caught up on what should my exact matrix should be. You should be using the GLM equivalent of these functions and getting a result that looks reasonably good. And then we can do things like change our frustum here of what is our aspect ratio in that dimension, what is our field of view in the Y dimension. And you can see how we get that effective different amounts of perspective here. We can start to change our near and far clipping plane, which should mostly have an impact in terms of what object is inside are resulting 2 by 2 by 2 cube or not. It is. He's quite hollow, unfortunately. Life's not good for him right now. And then separately from that, what I like about this utility is it does let you change. You can also just manually generate that structure. It's just, for me at least, it's a little harder to reason about what would look good or not look good. I mean, we can see it in this application, so you can kind of see as I change my left, right, bottom, top, and then near and far planes. But other than that, I think it's a little hard to reason about directly constructing the pyramid itself in the function versus calling perspective to specify field of view and aspect ratios. But then this also lets you play around with the orthographic views as well. So now we have him in the cube. But just because you're in a cube doesn't mean we're not manipulating our geometry. So by default, this would be an identity matrix, and next week we can look at how we wind up constructing an identity matrix. It's right minus left divided by 2, and top minus bottom divided by 2. So we're basically scaling everything by 1 here. But we can then change those values, and you can think of that in 2 ways, right? We can think of that as we're changing what the viewing volume we're specifying here, and the end result is, it's a little subtle, a little hard to see, is when we do so, that is effectively resulting in a scaling in X or a scaling in Y as well. So there we go. So for a lot of what we're doing, this type of application is nice to be able to see the equivalence of our modeling and our viewing of a scene, right? We could have generated a similar looking picture in the previous version of that application that was just changing scale factors and translate factors and things like that. But now when we're really thinking about ultimately projecting from 3D to 2D, we do have to think about where is our camera, where is it pointing at, what kind of camera is it? Is it a parallel projection or is it a perspective camera? And consequently, what should our matrix be at the end of the day? You just don't have to worry about manually setting entries in the matrix. You do have to worry about using these functions. And I think for almost everybody's first real 3D rendering experience and not the 2D stuff we've been doing so far, the very first thing you render is going to look entirely blank. Even though if all of your geometry is correct, if your matrix isn't set correctly, and this is a good example of that, right? If we were to set the default viewing matrix, it's a pain to drag it to -1.0. You set up this model, you have this perfect person model, you've done all the work in getting the geometry to be exactly the way you want it to be, and you set this default orthographic view, and that's what you get at the end of the day. That is kind of a common, debug experience when it comes to working with 3D computer graphics, because you have to then have the intuition for, okay, it's blank screen. Because right, you're not going to get this version on the left in general where you're seeing where my camera is and what my camera is looking at. This is the intention of this particular utility. How do I now set up my scene such that I can actually see what I'm looking at? The first thing to play around with would be depth. Play around with Z until you have a reason to believe. And just set a huge range if you're worried about it, Set a massive Z range, massive XYZ range. If it's too massive, everything will get squished into a very tiny box, but still look at what you have and determine, is it even capturing the geometry I have in my scene? And kind of work forwards from there and determine, okay, for the scene I want to view, what is a reasonable view? Where should my camera be located? It's probably shouldn't be located at the origin by default. It has to be placed away from your geometry, or your geometry has to be placed away from the camera to be able to actually see what you want to see something in your scene. Let's leave things here for today. I expect to see great progress on MP4 over the weekend and lots of people in Jeremy's office hours on Monday. And hopefully we'll have a fun demo day, okay? All right, thanks.